Deep learning, and in particular large language models like GPT-3 and BART, have dramatically improved the quality of text that AI systems can generate. And this is important because there are many applications in which language generation is needed. Large data stores are common to many organizations. And if we can present the content of these data stores in everyday language, this would make the data accessible to a large variety of people. In today's online world, we are overloaded with information, with large volumes of text that can't possibly all be read. Summarization of text, such as news, email, and financial reports, can help us to find information easily. Abstractive summarization selects the words and phrases to generate the information in a summary concisely. And there are many other applications where language generation is critical. It's needed for machine translation, for question answering, and for dialogue systems. But there's still a gap between how systems generate language and how humans generate language. Consider that we as humans speak with a purpose. We say what we mean. We choose our words and form our sentence structures intentionally, and we plan our longer text. These are still things which neural language generation systems cannot do. And yet, if we want to develop controllable language generation, these are necessary. So in this talk, I'm going to focus on two aspects of controllable language generation. Developing a system that can say what is meant, what is provided as input, and developing a system that can form sentence structures intentionally. So first, I'll talk about faithful generation from structured input, allowing a language generation system to be able to convey accurately what was intended as input. I'll then turn to abstractive summarization and talk about methods to develop a faithful system. And I'll close by discussing how we can develop a system to control word order in language generation. So I'll start with language generation in the context of task-oriented dialogue generation. And this is part of a shared task called E2E, which is run nationwide. And it will generate restaurant recommendations given an input meaning representation. So we see here a structured data or meaning representation. It contains a dialogued act here in form, a list of unordered attributes. So for example, eat type, and then attribute values. So for example, that the price range is more than 30 pounds. In this task, most models that have been developed are some form of sequence-to-sequence model where they take a sequence of attribute values as input and they generate a sequence of words or a sentence as output. They include beam search, which allows them to generate a variety of different possible outputs. So shown here is an output where the attribute and values are conveyed in the corresponding colored words in the sentence. So for example, the attribute, the name, the vaults, and the eat type is conveyed in the subject of the sentence, the vaults pub. So why does a sequence-to-sequence model fail? It typically fails because idiosyncratic meaning representations are not well modeled. So these are meaning representations that occur rarely or perhaps not at all in the training data. And in these cases, we will see that some attribute values in the meaning representation provided at test time never appear in the NBEST list of sentences that are generated. So shown here, we have an input about the restaurant Alimentum, and it says that it's near the Burger King. But in the top 3 best outputs, we never see that expressed. Instead, we see generated that it's near the Express by Holiday Inn, the Alimentum is near the Yippee Noodle Bar, or it's near the Raja Indian Cuisine. And this is problematic because this means the output is incorrect. It's not expressing the meaning of the input. And in fact, if we were to look at the best 256 output sentences generated, we would never find that attribute. Again, very problematic. So how do we obtain a faithful generation model? So we've developed work which was presented at INLG, where we use data augmentation to create diverse meaning representation utterance pairs that were not seen in the training distribution. And we do this by making use of noise injection sampling and self-training. We use noise injection in combination with the original sequence-to-sequence NLG model, which is unfaithful, to create novel utterances. These are off the training distribution, and yet they're syntactically well-formed and fluent. And we combine this with self-training, where we next retrain the language generation model on a combination of the original training data and the synthetic data generated from the unfaithful NLG model. So shown here is an example training instance from the training data, where we have the meaning representation on the left and a sentence that would be generated for it on the right. We use this to train a base speaker, where the base speaker is given the meaning representation and uses the sequence-to-sequence model to produce a text output. We combine this with a listener, which is a parser which can produce meaning representations from the text that it hears to produce another meaning representation. Now, we then add Gaussian noise to the base speaker model, and this encourages the utterance that is generated to be outside the training distribution. So now we have a novel utterance which doesn't correspond to the input meaning representation, and the listener will produce a new meaning representation which does correspond to what was generated. And this pair, the novel utterance and the generated meaning representation, are collected and used to create a synthetic data set A. Now we retrain the meaning representation to text sequence-to-sequence model on the combination of the original data set and the synthetic data set A to obtain the faithful speaker. We can see the algorithm here, and we'll see that in the first step where we sample meaning representation from our data set, here at the bottom, you can see this is an inform about the restaurant The Eagle, which is family friendly and has Italian food. Now we use noise injection sampling to generate an utterance from that, and you can see that the utterance does not match that meaning representation. We have an utterance about the Waterman, which is located near Burger King. And the listener then uses its parser to create a meaning representation corresponding to the sentence about the Waterman. So we can see in the green that now we have name equals the Waterman. So faithful generation is done by training a new sequence-to-sequence model on the original training data plus the synthetic data, which is created, as I just described, described. And this new sequence-to-sequence model is the faithful speaker. Okay, so to evaluate how well this works, we use metrics that are used in the end-to-end challenge task. And these are metrics that are typically used in language generation: N-gram overlap metrics, BLEU, which comes from machine translation and is precision focus, and Rouge. Here we use Rouge L for longest common substring, which is recall focused. And to give you an idea of how it works and why these could be problematic, a generated sentence is compared against a gold standard reference to count the number of overlaps in words, bigrams, or longer sequence with the reference. The first generated sentence at the top, we can see, has high Rouge because many of the words overlap with the reference, in fact, all except for one. But it has a high semantic error rate. And by semantic error rate, we're counting the number of missing, incorrect, or added attributes normalized by the number of attributes. The second example has a low Rouge, although it actually means the same thing as the reference. It just happened to use a number of synonyms. So in our results, we see the base speaker and the faithful speaker at the bottom, and we compare this against some state-of-the-art baselines at the top. We can see that the base speaker appears best according to the N-gram overlap metrics, but it has the worst semantic error rate. The faithful speaker is competitive to the baselines on Rouge and BLEU, but it's worse than the base speaker. However, it has the lowest semantic error rate, and one of the variants of the parsner, the rule-based one, achieves a 0% semantic error rate. We also did a human evaluation where annotators compared 100 test set model outputs against a human reference with respect to correctness and linguistic quality. And we found that the base model was worse than the human reference on correctness 4% of the time and on linguistic quality 3% of the time, while the faithful speaker was worse on both correctness and linguistic quality 0% of the time. So what have we learned? Well, we've learned that sampling and self-training can improve the correctness of language generation models. Even greedy decoding can be more semantically correct than sophisticated models. And fluency and grammaticality of self-trained models can be maintained. Finally, Rouge and BLEU are lacking in terms of measuring how faithful a system is. So let's turn to summarization. Is abstractive summarization also unfaithful? And the answer is a resounding yes. Previous work has shown that 30% of summaries generated by neural sequence-to-sequence models are unfaithful. And we show an example here from a BART large fine-tuned model where the input says, talks about Klitschko, who doesn't have the legs, and goes on to say he has a chink in his armor, where the BART large model instead generates that Anthony Joshua has a chink in his armor. Anthony Joshua is mentioned in the input, but he is not the one. So we have an error, and this is problematic. So in this work, which was done at Amazon by a group led by Nan Feng, we show again that BLEU and Rouge are inadequate at measuring factual consistency. And we propose a new computationally efficient metric based on question answering, which we call quals. The idea is that if we can generate questions about the summary, answers generated from the summary should be equivalent to answers generated from the document to the same question. Quals is similar to a previous metric that was developed for summarization evaluation, also based on question answering, called CAGS, but Quals is 55 times faster than CAGS. And this means that quals can be used as a training objective, and we use it with a contrastive learning method. The quals metric looks at the averages the difference in log likelihood of question-answer pairs generated from the document and question-answer pairs generated from the summary. And we can see this in our diagram here. We have a question-answer generation module, and the summary is fed into it to produce question-answer pairs. We compute the log likelihood score from the summary for each question answering pair and the log likelihood score from the document. Our question answer generation model, QAGen, is also a sequence to sequence model. As an encoder, it takes the input document or summary and generates these question answer pairs. So, for example, it would generate, for the example that we just saw, the question, who has a chink in his armor? And the answer from the input is Klitschko, while the answer from the summary is Anthony Joshua. In contrastive learning, we train an initial seek-to-seek model using maximum likelihood expectation. We then construct positive or factually consistent summaries from the ground truth, and we construct negative or factually inconsistent summaries from top case sampling. We then maximize the log likelihood of generating positive summaries while minimizing the log likelihood of generating negative summaries. For our experiments here as data, we generate summaries of single news articles, making use of a corpus called CNN Daily Mail, which is widely used, and where the summaries tend to use more words from the input article. We also use the XSUM corpus. Here, the corpus is created by taking the first sentence of a news article from the article to serve as the summary. And as a result, this corpus has summaries that are very abstractive, but they're often actually not factual. As evaluation metrics, we also use Rouge, but we use CAGs to measure faithfulness. And in our results on XSUM, we can see in the second column that where we compare quals with contrastive learning against BART large trained with maximum likelihood, we can see that quals yields 4 points improvement on CAGs and has only a slight drop in Rouge. On CNN Daily Mail in the bottom table, we can see that quals uses 2 points improvement in CAGs over BART large. And Rouge scores also improve. We did a human evaluation as well, asking people whether summaries generated by quals contrastive are better than BART MLE along 3 dimensions: factuality, informativeness, and grammaticality. And we see that quals contrastive does better along factuality and informativeness and is equal on grammaticality. Shown here are a couple of examples from the qualitative analysis that we did. For example, for input 1, the document said that it found 705 emails and passwords. MLE generates more than 700,000 emails and passwords, clearly incorrect, while quals contrastive is able to retain the 705. In the second example, the input tells us that Paul Bramley died when Lubis locked the captain out of the cockpit. In MLE, what is generated is that Paul Bramley died when Lubis locked him out of the cockpit, while in quals contrastive, we correctly get the captain being locked out of the cockpit. So what have we learned? Well, we've seen an efficient metric to calculate question answer accuracy is effective when paired with contrastive learning. We are able to improve factual consistency over a BART large model trained with MLE. And we've also seen that traditional metrics like Rouge are not adequate in themselves for faithful summarization. So let me turn now to the last problem, that is controlling word order in language generation. So what about other types of control that we might want to have? So shown here, we have two different ways of verbalizing the same meaning representation as input. In the first, this might be appropriate to a question, what is a roamie? A roamie is a coffee shop in the city center. While the second phrasing might be more appropriate for a question, where can I get coffee? For coffee in the city center of the city, try a roamie. If we can control order in language generation, then we can implement cognitively plausible models, for example, following centering theory, where we can convey the intention of the speaker. We can also more easily generate diverse sentences, and we can reliably use neural language generation in different settings. So we propose a method called alignment training, where we want the output to follow the order of the attributes in the input. So instead of what's shown here, we want a system, we train a system so that it generates outputs such as the following the order of the input attributes. And we find that with alignment training, we can yield controllable generation. So we can control what our output looks like by using the correct ordering of attributes on the input. At test time, however, we don't know what the order of the attributes are. So we propose two planners for alignment training, which generate an appropriate order or desired order of the attributes. In one, a bigram utterance planner, we use the training data to estimate a bigram language model over the attribute value sequences. And in the other, our neural utterance planner, we train a seek-to-seek model to map arbitrary linearization of attribute values to a realization plan. Here we do experiments again on the end-to-end data set of restaurant reviews. This is quite a large one. And we also experiment with a smaller data set called Vigo, which is about laptops. We experiment with 3 different models to see if alignment training will work with an arbitrary model. And again, for metrics, we use Bleu and Rouge, semantic error rate, and we introduce a new metric, order accuracy, which counts the number of times the generated utterance follows the input plan. We compare this with 2 baseline ordering strategies, one which simply orders the attribute value pairs in increasing frequency from the training data. And this guarantees that the same ordering of attribute values occurs every time they appear. And then we also experiment with random ordering of attribute value pairs. This gives a lot of variation in plans. And in our results on semantic error rate, alignment training, which is in the green, reduces semantic error compared to our baseline strategies. It approaches 0 semantic errors in a large data setting. For Bleu, we see that we maintain a high Bleu for the different alignment training strategies, with the exception of BART in a small data setting, Vigo, shown on the right, which has lower Bleu than when the trained from scratch models. However, BART also has lower semantic error, so we need to be careful when making judgments from Bleu alone. On order accuracy, the 2 alignment training planning strategies are shown in green, and we can see that order accuracy is higher than in a human model. So our lessons learned, can we make an arbitrary sequence-to-sequence model controllable? Yes. Alignment training works regardless of architecture. How robust is a controllable seek-to-seek model? Well, performance drops on random plans, but I did not show here, but we can mitigate that with data augmentation. And we also see that BART maintains controllability in both large and small data settings. So overall, in summary, we've demonstrated approaches to control faithfulness in both language generation and summarization. And furthermore, we've shown that alignment planning can be used to control word order in language generation. For both problems, we see that traditional automatic metrics such as bleu and rouge are inadequate. And we've also seen that data augmentation is a good strategy for multiple problems. If you'd like to learn more about machine learning, there are a variety of different resources that you can access shown here. Thank you.